So for this first problem, we have an airplane, and it has thick aluminum walls, and we want to find the rate of heat transfer of the entire body for a 1D analysis and using a resistance network. So they're two separate portions of this problem. So first, the resistance network, we have to find area, you want to find your resistance of your inner portion, your resistance of aluminum, and the outer portion, and then you add those together because they're in series. So then you can find your Q dot, which is your change in temperature, and then over your total resistance, so you get 394 watts. And then to find the temperature, you can find T1 by saying T infinity 1 minus T1 over R, the resistances, and you get 4.85 degrees C. So for our 1D analysis, you can just say Q is equal to H, your area, and then the change in temperatures. So you can see that without resistance, there's a much higher heat transfer. So the aluminum walls are a lot better at insulation than in the 1D analysis. So this next portion, we have an energy balance on a spherical volume shell element. We're going to skip this because it was given 100% in the last project. Next, we have a droplet of water. So that's released into space, and we have initial temperature of 20 degrees. And we want to find the final temperature of the water droplet if it is a black body. So we have all these knowns. Pretty easy problem. We set mass equal to rho v. We get 1.368 times 10 to the negative 9th kilograms. You plug that in. MCP delta T is equal to your Q radiation. So you get your final temperature is 2.8 times 10 to the 27th Kelvin. Next, we have a really long aluminum bar, which is heated in a furnace, and we want to find the heat transfer and the temperature the rod needs, or the time the rod needs to reach 500 degrees Celsius. So our knowns are the length, diameter, different properties of aluminum, and we want to find the time to heat the bar and the heat transfer. So we have the lumped analysis, we have our one-term approximate solution. So we find the Biot numbers for a plane wall and long cylinder, and then get those values. We can assume tau is greater than 0.2 because it's given in the problem statement, and then you multiply those together and you get your temperature profile. Then you can solve for your time, which is 0.07 seconds. We then want to check that then tau is greater than 0.2, which is true for both. And then our total heat transfer is equal to m rho v. Our mass flow rate, or our mass is 6.79 kilograms. Then our Qmax is 2,878 kilojoules. Total heat transfer you can find by taking the ratios of our heat transfers from each of the analyses. And we get 1 and 1.98. And then our total Q dot is then 5,698 kilojoules. Next, we have a shell and tube heat exchanger, which is fed by a stainless steel long wire heater. So the length of the heater is 1 meter, a whole bunch of other givens, and we want to use the LMTD method to determine the length of the shell and tube heat exchanger. We're given flow rates and what the hot stream and cold stream are. So we will draw a diagram here. We have our heater, and then the shell and tube exchanger. We have assumptions. 1D heat transfer in radial direction, convection at the outer surface of the heater. So to find the 1D steady state heat transfer in the R direction, we get this equation. Then our boundary conditions are convection at the outer surface because that's given in our problem statement. Also, it's a heater, so there's water on the outside that will cause convection. And our thermal symmetry, it's a cylinder, that's just because at the center line it should be equal. So you integrate once, get your boundary conditions, integrate again, then use our first boundary condition where R is equal to R naught, and we get R is equal to 0, so we get our equation here, plugging that back in. Then our centerline temperature can be solved for by taking the above equation and plugging in our values, and then R2 is equal to 0 because that's the center line, R is equal to 0, so that's the center line. So you get 137.9 degrees C. From there, we have our rate of heat transfer, which is Q is equal to MCH TH in minus TH out, and then Q dot is equal to that. Then we can solve for our heat transfer of the other stream, and then you get TC out of 70 degrees, so that's our first thing. We then want the change in temperature limit, and you get 76.1 degrees C based on the what we calculated for TC in and the givens. Then our volume is equal to m dot over rho A, and that's 3.35 times 10 to the negative 4th meters per second. Get our Reynolds number greater than 10,000, so it's turbulent flow and it's fully developed, and our Prindle number can then be solved for. We have our Nusselt number, and then we can solve for H, U, and then Q dot, and we get 5,406 meters. Our last problem is a cylindrical membrane with a feed stream of carbon dioxide and oxygen. There's a givens on all the streams. We don't have a second waste stream, so that's a little bit different. And first you can solve for the time for the membrane to permeate, and that's 14.2 hours. Then our driving force is the change in pressure of CO2, so that's 20.4 kPa based on our log limit of change in pressure. Lastly, we have a rate of heat transfer for two different systems. First, we have a heater with hot air coming through the center. We have our properties. We want to solve for H. Our delta T limit is again used, and we get H is equal to 3,057.8 watts per meter squared times K. Can then solve for Q dot by using the values we've solved for. Part B is separate. We have a solar collector, and we want to determine with and without wind what the rate of heat transfer is. So we can use our table A-15 to get our properties of air at the average temperature 25 degrees C. And then our critical length can be solved for based on the fact that it is a square or a rectangular solar collector, and we have the width given. And then we use our Nusselt number, you get your H, area, and then solve for Q. And then with no wind, it's completely different analysis because it's natural convection. So we use our Rayleigh number, and we get 5.63 watts. Basically the same idea, except for using height and the length corrected instead, which is area of surface of a perimeter.